Okay, we're gonna try that again since apparently I just gave the entire talk to myself and no one else. So second time, same as the first, a little bit louder, a little bit worse. All right. Thank you for coming or possibly sticking around through an entire failed attempt. So I'm Alex. I have been quite fortunate to have a fairly eclectic career. At various points, I've been a security engineer, an SRE, somebody who works on antitrust litigation, and one of the things I try to do as I take increasingly bizarre jobs is try to learn from the people I work with about kind of the different philosophical tools they use in their work, and then I try to cross-pollinate them. So that's what the goal of this talk is. We're going to dive right into sense-making and redundancy. Sense-making is not a phrase that many people have probably encountered. I had not either until a few years ago. Sense-making is the process by which individuals and groups process information and ascribe meaning to it. So it is making sense of our environments. If you hear a loud bang and then a few minutes later you hear a siren, sense-making is the process by which you decide those two things are related. So the concept of sense-making was invented by a psychologist named Karl Weick, and he wanted an analytical tool to understand why organizations make the decisions they do, and he was particularly interested in how we analyze conflicting information. And this kind of intuitively makes sense. If all the information points in the same direction, what it means is probably obvious, but when the data is all over the place, how do we describe a meaning to it? So to make matters kind of even more complicated, not all information is the same. Some information is explicit, other information is implicit. Some information is about things that are happening. Other information is observations of things that don't appear to be happening. So imagine you go out for lunch with a coworker and you take a long lunch and they spend the entire time complaining about how busy they are. What does that mean? Are they lying about how busy they are because they think other people value busyness? Are they very busy but procrastinating? Are they trying to get you to take some work off their plate? Any of these guesses and many more fit these facts because the facts are not particularly consistent. How each of us decides what we think the evidence means is the essence of sense-making. And sense-making is a concept that once I was introduced to it, I began to see everywhere. So in 1949, a wildfire happened in Man Gulch in Montana, and in 1983, Karl Weick, the same psychologist, wrote about it in a paper titled The Collapse of Sense-Making in Organizations, the Man Gulch Disaster. And an incredibly abbreviated version of what happened is that a group of 15 smoke jumpers parachuted in to fight the fire, and when they arrived, they connected with another smoke jumper who was already on the ground, and they made a plan to collect their equipment, to eat, and then start out working on the fire. Within 2 hours, the fire had overtaken them and 13 of them died. How could it have been that these smoke jumpers were all making a plan to eat lunch before fighting the fire, even as they could see the smoke from the fire all around them? Weick's answer is that there was a breakdown in sense-making. The conflicting signal of the smoke and the fact that none of their peers thought they needed to proceed immediately led to the conclusion that the situation was less dire than they thought. They favored the implicit evidence of no one else seems that concerned over the explicit, I see smoke. For Weick, most of the sense-making we do is about creating narratives, stories that tie everything together. Stories are powerful. They build culture, they allow us to transmit information amongst ourselves in ways that raw facts cannot. But just because something makes a good story doesn't make it true. My colleagues know that the fire is close. That's why we have time. My colleagues know the fire isn't close yet. That's why we have time to collect ourselves and eat lunch before we start is a good story, but it's not reality. In any given situation, there will be many stories that cover a portion of the facts that appear there'll be any number of stories that appear to cover a portion of the facts, but most of those will not be accurate. Probably many listeners are familiar with Daniel Kahneman's Thinking Fast, Thinking Slow, based on research he did with Amos Tversky. In his book, Kahneman describes System 1, or Thinking Fast, in which we all make snap, implicit judgments based on heuristics, and System 2, Thinking Slow, where we process information and reach rational, analytical conclusions. We like to think of ourselves, and people in general, as mostly operating in System 2. But in reality, the vast majority of our time is spent in System 1, thinking fast. And in fact, an awful lot of what we do with System 2 is meant post hoc rationalizations for judgments we made in System 1. So to connect Kahneman's work with Weick's work, when we have conflicting information, we need to reconcile it. The process of that reconciliation is sense-making, which we largely do by forming narratives. But a lot of the narratives we form are constructed through our System 1 thinking fast heuristics, which we know are subject to a bunch of cognitive biases that lead us to incorrect conclusions. We'd like to think of ourselves as rationally and systematically operating in System 2, considering all of the conflicting evidence and making judgments on which evidence is most credible, and using that to reach conclusions. But that's not the default way humans operate. What we mostly do is use the prodigious skills of our System 2 to justify impulsive conclusions and narratives System 1 put together. And that's the essence of how we get a sense-making failure. So why do engineers need sense-making? What's the relevance of this to our work? Well, presumably we'd all like to do a good job, to write software that works well. But how do we know if we're doing well? And what does it even mean to do well at building software? Some of the things we care about are building features that users want or not having bugs that ruin their experience. But we also care about things like reliability and uptime and performance, which users rarely ask for explicitly. And we often have other objectives like security, which we tend to only notice when it's missing. It goes without saying that sometimes these desiderata are even in tension. Adding lots of features makes it more likely that they'll be buggy. Trying to do things too cheaply adds risks to uptime. Trying to move too quickly maybe adds risks to security. In pursuing these goals, we get feedback from a ton of different places. We have our own perceptions of how good we think our code is. We have our peers' feedback, both the things they say and the things they don't. We have some quantitative metrics, things like uptime or latency or test coverage. We get feedback from customers in the form of, customer reviews or feedback they give us directly. We have customers' revealed preferences. Do they actually buy our product? If things go really south, we might get feedback in the form of inquiries from the media or government regulators or a whistleblower. And we need to somehow integrate all of these disparate forms of feedback to develop views on questions like, have we built a good product? Have we built our product well? How secure is our product? How performant is it? How reliable is it? Are we doing a good job? And this is the kind of tool we use sense-making for, to answer hard questions from conflicting evidence. And this is why I think we need to study sense-making, because if we don't, we're apt to make judgments about these questions based on what makes the nicest narrative and not based on what the evidence best fits. All right, bit of a gear shift. What is redundancy? I won't belabor this. So redundancy is any time you have multiple mechanisms to accomplish the same task. Sometimes multiple mechanisms are more than one copy of the same mechanism. For example, multiple web servers behind a load balancer. Other times redundancy is multiple mechanisms that are different in kind. For example, a defense in-depth security design. But our overall thesis is always that we accomplish our goal even if one of the mechanisms fail, which we'll call a partial failure. And we have tons of examples we encounter all the time. Offsite backups, database replication, load balanced web servers, defense in depth, privilege separation, sandboxing. We build systems that are more reliable than the sum of their parts. That's the theory. So when we're designing a redundant system, how do we think about its effectiveness? So let's walk through an example with database replication. We've got a primary database and a set of read replicas, and if the primary becomes unavailable, we fail over to one of the read replicas. Very standard setup. When the database primary fails, is that okay because we have redundancy to keep the whole system working and hide the users from an outage? Or is it a problem because the database primary really shouldn't be failing? Do we declare a production incident because of the failover? Do we hold a postmortem? Do we publish it on our status website for users? Clearly the point of having redundancy is in some sense to make it okay to fail. At the very least, to make it not catastrophic. So we shouldn't treat it the same as the database primary failed over. So we shouldn't treat it the same as if the database primary failed and we didn't fail over, right? On the other hand, if the database primary is failing over once an hour, it seems like that's probably a problem, even if it never triggers a production outage, right? This tension between the point of redundancy being to make failures okay, but at the same time, the intuitive recognition that something probably shouldn't fail that way is kind of the core thesis of this talk, which is that redundancy frustrates sense-making. I started talking about how the core of sense-making is how to resolve conflicting inputs, and that is exactly the point of redundancy, is to give us conflicting inputs. When redundancy works well, we have a system where the overall system performs well, say no user visible outage, but an individual component was not performing as it was intended. So we're just inevitably getting conflicting inputs that trigger our sense-making systems. And because humans process these conflicting inputs by finding narratives that make it work, we often miss when our redundant system has a serious problem. And that leads us to make bad decisions about how to design and maintain systems. And I want to show two examples with that kind of failure. So the first one is STS-51L, which is better known as the final disastrous flight of the Challenger space shuttle. And most of what I have to say here is drawn from Diane Vaughan's excellent book, The Challenger Launch Decision. It goes into all this in a lot more detail. So it's fairly well known among space enthusiasts that the proximate cause of the Challenger failure was the failure of the O-ring in the solid rocket booster due to low overnight temperature. What you may not know is that the O-rings were a redundant component. There were two of them, and the design was that a failure in the primary O-ring could be compensated for by the secondary O-ring. And on previous flights, the primary O-ring had in fact experienced problems known as blow-by, and these experiences had given the engineers at both NASA and Morton Thiokol, the contractor responsible, confidence before the final launch that even if the O-ring had a problem, it'd be okay because there was a redundancy. I am confident many of us have used this exact type of reasoning before. When considering whether an operational change was safe, we look to see if we've done something similar before, and if we have, that gives us confidence that it will also work this time. But if we look at this through the lens of how redundancy impacts sense-making, what we see is that the previous experience with redundancy appearing to work gave confidence that the failure in the primary was okay. Which may have been true right up until the same cause also led to a failure in the secondary. Redundancy led to the attitude of failure is okay without a framework for assessing when failures in the O-ring stop being okay. One thing I like to draw attention to is that when we assess the reliability of a primary, we often do things like run it under a bunch of scenarios and see how it performs. But to assess the reliability of a secondary, in situation, we need to test a bunch of scenarios in which the primary has already failed. Testing a system under conditions where there is already a partial failure is the classic sort of thing we're very, very bad at as engineers, right? And we see this in things like the Jepsen tests of distributed databases, where many distributed databases have concurrency properties that simply do not hold in a partial failure scenario because they're very difficult to test. We just intuitively, when we see a situation like, we've constructed a failure for the primary, we think, we should make the primary resilient to that, instead of focusing on what we're trying to do, which is make the secondary resilient even in the face of a failure in the primary. Now I'm going to go to a second example, which will probably be more controversial, at least with a software engineering audience. So, and that is sandboxing in web browsers. So once upon a time, everything the web browser did, from rendering the user interface to parsing network protocols to running JavaScript, happened in a single process. And so when any component in the browser had a vulnerability that allowed executing remote code, you could you get remote code as kind of the user. There was nothing stopping you from executing code on that user's machine, no matter which component it was in. Eventually, it was recognized that this was pretty untenable, and browsers were refactored to be split into multiple processes. Most importantly, there was a split between the renderer process that executed and rendered HTML, CSS, and JavaScript, but was aggressively sandboxed to have no operating system permissions, and then a parent process that did not render individual web pages, but had kind of full permissions to do things like access files or play sounds. And then the renderer process would use IPC to ask the parent process to perform tasks on its behalf, and the parent process could do permission checks. And so this was really pioneered by the Chrome security team, and this was kind of definitively a better security model. And if we unpack the core assumption, is that there's simply too much code in the renderer process to meaningfully secure. But the IPC attack surface is much smaller, so we will be able to effectively secure it. Even if you get code execution inside the sandbox, you won't be able to break out. And for the first few years of browser sandboxes, this theory really appeared to be a strong one. While browsers continued to see lots of vulnerabilities in the renderer process, there were hardly any vulnerabilities reported in the parent process in that IPC code, and that proved that the sandboxing model worked. And then in the mid-2010s, something interesting happened. There started to be a lot more vulnerabilities reported in the IPC systems. The parent process no longer looked quite so invulnerable. What had happened? Well, my theory of what had happened is that testing HTML or JavaScript or fuzzing image parser is much easier for security researchers than testing an IPC system. Testing an IPC system reliably is incredibly stateful. It requires a partially running browser in different situations. It's just not a sort of thing that's easy to build a test bed for as compared to like a very stateless PNG parser. So that as a result, the parent process and the renderer process were getting radically different amounts of security research, both from external researchers and within browser companies. The observation that there were fewer IPC vulnerabilities was made without knowing the denominator of how much security research was actually being applied. Once people started actually testing IPC more in the late 2010s for a bunch of different reasons that aren't the point of this talk, it turns out it wasn't quite as secure as we've been assuming. We tricked ourselves into overestimating the security of web browsers because we had confidence in that redundancy mechanism, the sandboxing mechanism, even though we didn't have a great understanding of its effectiveness. In many ways, this is a story that's very similar to the story of the Challenger. We didn't do a good job assessing the redundancy mechanism, so we reached bad conclusions about the overall system's security. So what should we learn from this? Well, one takeaway I really want people to have is that redundancy impacts sensemaking. That when you are building a redundant system, you have to be thinking about what kinds of inputs you will get when it is running, and how will you know if it is running well or running poorly. More broadly, though, I think it's just critical to understand the concept of sensemaking in general, and to notice when what we're doing is analyzing conflicting evidence, as opposed to just looking for which way the evidence points at all. Analyzing conflicting evidence requires fundamentally different patterns of thought, and getting ourselves out of the autopilot mode that, we all spend most of our lives in is critical to doing it well. For redundant systems in particular, we need to know how to measure and all of their components, including the kind of failover mechanisms itself. And forcing ourselves to assess the reliability of things besides the primary is really our only way to know if our redundant mechanism is working as intended. And this means forcing ourselves to test redundant systems kind of in the situations of being in partial failures, the kind of situations that are classically hardest to test. We also just need to have clear theories about what a redundancy is for, and we need to hold ourselves against them. Is the database replication intended to allow the primary to fail all the time, or is it a measure of last resort? If it's really designed to allow the database to fail all the time, that means testing it like something that's intended to be used all the time. That means taking our database primary offline with something like Netflix's Simian Army, and making sure the mechanism works in production. On the flip side, if our failover mechanism is intended for catastrophes only, we need to act like it. If we find ourselves relying on it a lot, that's a red flag. We need to be holding postmortems, figuring out what actually triggered the underlying failures in primaries, kind of all the things we would do if it had actually produced a user-visible outage. Lastly, my hope is that for you, like for me, once you kind of are familiar with the concept of sensemaking, you'll begin to see it everywhere. All of the situations where what you're doing is fundamentally processing conflicting information, and start seeing all of the different possibilities ahead of you, and not just kind of the one theory that kind of makes the best story. In addition to the books by Diane Vaughan and Daniel Kahneman that I referenced, I also recommend Philip Tetlock's Super Forecasters if you're interested in learning more about these types of cognitive processes. Thank you very much.